Then we start the recording. So welcome on to this lecture. This is the fourth lecture in that series of 5 lectures on AI for Good, based on this forthcoming book, the AI for Good handbook. So last time we talked about cities and communities. Today will be about energy, and the last lecture next week will be about nature. Okay. So let me go to the. So I'll talk about 30 minutes, 45 minutes. Then we'll open it to Q&A. So you can always sign up to the meetup, or you can invite friends to sign up. So the outline today, so we'll talk, I'll go briefly this time because we talked before about the Sustainable Development Goals. There are 17 of them. We talk about the state of energy briefly, to give you the big picture on the energy sector. We talk about the specific SDG, so Sustainable Development Goals targets, how to manage the energy sector, and how AI can help manage the energy sector, and go over some case studies and conclude. So today is the theme of energy is the goal number 7, right? So we went over poverty, hunger. We had a speaker to talk about healthcare. Last time we talked about sustainable cities and communities. Today is energy, and next week will be about sustainable SDG 14 and 15. In fact, I'll combine them to so it'll be like nature, life below water, and life on land. So all these goals are aspirational, right? It means that there's no nobody is mandated to achieve these goals, but this is kind of a common purpose for the international community. So let's go over the energy sector. So as you know, so energy is used everywhere, like in industry, power generation, transportation, buildings, agriculture, food production, services, and so on. Now, without energy, we wouldn't have an economy, at least a modern economy, right? And without energy and the innovations, such as steam engine, electricity, generation and distribution, right? Steel making, combustion engine, and so on, humanity will be in a very different place. So we should be reminded of that. So energy use, so we take it as given that we use a lot of energy, but as many countries are growing, they're going from like low income to middle income and to high income countries, they're consuming more and more energy, right? So richer countries like us, like in the US and Europe, can consume much more energy per capita, right, than poorer countries, right? And the most striking example is a country like China, right? They have increased also the energy consumption per capita, right? Because you go over maybe 10, 20 years ago, they were riding bicycles, and now they all have cars, or they have AC at home, or so on. Still, we have to remember that hundreds of millions of people do not have access to a reliable source of energy. Right? So there's no electricity grid, and they don't have power, most of the day. And so they use like low-tech solutions, for instance, for cooking, such as wood burning, for heating, cooking, and for them with damaging effects on the health and the environment, so especially in Africa, right? So women will spend a lot of time, gathering wood, and burn it, and so on. It will be very time consuming. Energy sources today are mostly like fossil fuels, right? Coal, natural gas, oil, biomass, and they release greenhouse gas emissions, right? CO2 and methane. and when they are burned, to generate heat and pressure to be converted into energy. Other sources of energy do not emit carbon, right? So some renewable energies, nuclear fission, dams, some forms of energy are consumed directly, right? Like in cars and so on. They don't need to be transformed. So that's why what's happening to the energy sector is so important for for the rest, right? For climate change in particular. So so the United Nations have attached these SDG targets to that goal number 7, right? So for the energy sector. So I'll go over them briefly with you. Yeah. So by 2030, right? So this is in 8 years. Right? Enhance international cooperation to facilitate access to clean energy research and technology, including renewable energy, energy efficiency, and advanced and cleaner fossil fuel technology, and promote investment in energy infrastructure and clean energy technology. Well, the clean part is really because of climate change, right? Because of this, oil, coal, and so on are big emitters of CO2. By 2030, expand infrastructure and upgrade technology for supplying modern and sustainable energy services. So sustainable, it's like the same as clean, for all in developing countries, in particular least developed countries, small island developing states, landlocked developing countries, in accordance with their respective programs of support. The International Energy Agency is the international agency focused on energy, forecasting energy demand, energy supply, energy prices. So they do very important work. They have published a report last year to show a pathway to reach what they call net zero. So net zero in terms of CO2 emission. Right? So it means that net, like if you look at like all the carbon emission on all the ways you can reduce the emissions is like we reach net zero by 2050, right? And limit the temperature increase to 1.5 degrees, as like a warmer temperature is causing climate dysfunctions. This is an ambitious plan requires significant change in the world energy mix, with massive expansions of renewable energy, right? And it also depends on technological innovations, such as like batteries for energy storage, hydrogen production, carbon capture, utilization, and storage. IEA proposed a set of priority actions. Right? So here governments need to set milestones on the pathway to net zero. So it's asking all countries, including the US, Europe, China, India, and so on, to say what's their plan to reach net zero by 2050. They include like the milestone should include the moratorium on coal plants, right? No new oil and gas fields approved. Phasing out of coal plants in advanced countries by 2030, right? So it means that you close all the coal plants that you have today, right? So it's not only like no. You don't build new coal plants, but you shut down the current ones, right? No new internal combustion engine cars by 2035. So I believe that the European Union is following this path, and California too. I think recently they made an announcement, right? So you do. I mean, you still can drive combustion engine, but you cannot buy new combustion engine cars, I think. And you have net zero emissions electricity by 2040. Right? We increase investments in clean energy and energy infrastructure to an amount of like a staggering like $5 trillion per year by 2030. Address energy security risk, right? Particularly the green dependency on critical minerals, and increased concentration of oil production. Right? So oil production is mostly in the Middle East, right? Or in Russia and some particular countries. And minerals, you can think about batteries, right? We all shift to EV, to electrical vehicle. we have to rely on lithium, on some rare metals, so that sometimes you can find only in in a few countries. Then the last point, reinforce international cooperations, but by accelerating innovation, developing international standards, and coordinating to scale up clean technologies needs. Right. So the theme is really like sustainable energy, clean energy, right, and reduce dependency. Right, and we see what's going on in Russia and so on. So it's causing big problems, especially in Europe today. So how AI? So today, the talk is really about AI. So how AI can help manage the transition for the energy sector. So if you have attended the previous lectures, you remember you have that peacock, right? You just remember the peacock, the animal. It's not spelled the same. It's like you have like 4 dimensions of how you can where AI can be applied: prediction, coordination, optimization, and control. PCOC, peacock. So prediction, right? So on the supply side, so these are all the things that AI could do potentially. They do today, or it does today, or it could do tomorrow. So on the supply side, right, AI can help locate energy sources, such as the best places to set up wind farms or solar, like photovoltaic installations, fossil fuel production. It can help detect like methane leakages, or reduce pollution. It can help predict energy production and cost based on inputs and factors such as weather and climate. For solar PV, it could be based on sun exposure, right? For wind farms and the weather, cloudiness, so weather pattern could predict the electricity production from wind farms. For natural gas, it will depend on international market prices, transportation costs, pipelines, availability of pipelines, and so on. AI can also predict greenhouse gas emissions, right? Using data from sensors and satellite imaging. AI, I think, can also detect like methane leaks, I think, from satellite today. On the demand side, you can predict demand of different sectors based on the economic activity, weather, seasonality. For instance, the temperature will drive demand for electricity, right? So in the summer, warm weathers, you could predict, the usage of AC units, right? In the winter, it's very cold. You can predict more usage of heating fuel or gas. Coordination. So AI can help identify the factors driving supply and demand, right, in energy markets. It can help with planning capacity for energy supply based on future demand and the energy mix of supply. So you can forecast the next day demand, but also like the demand in 3 months, 6 months, or a few years. For intermittent producers, right, they could be complemented with less intermittent ones, and then you need coordination between the two, right? So, for instance, wind farms will produce electricity only when you have wind, right? And solar, like PVs, will produce electricity only during the day, not at night. So this kind of thing. So when there's clouds, you cannot produce electricity from solar panels, right? So this you need coordination. I could tell you. Optimization. So coordination. The next step is the optimization. Right? You optimize the short-term production on demand. We'll go over an example of this. Can help optimize, the operations, maintenance schedule, for instance. All these machines also need to be maintained, repaired, and so on. Optimize the cost, right? What is the best time to use some means of production, and can optimize along the value chain, right? And identify the cost efficiency. Control. So this is like less common, but you start to see it. Can control the short-term production and demand in energy markets. So it is like you can say like intermittent. Some producers could be launched automatically. That as the price of energy goes up above certain level, you can start to produce electricity with some expensive means of production. AI can monitor and control the inputs and outputs on the overall operations, efficiency, safety, and security. Right? It can help operate the power grid. We are going to talk about this in one of the case studies. And can help for real-time pricing of energy. Right? So when energy supply is low, the price you have to charge a higher price, right? And it can be so it can be decided by the market, or you can also decide on your price, right? So three case studies. One on the power grid. The second one would be on the energy demand response, right? So how do you manage the how do you price energy, so that you get the adequate demand response from the consumers. And the last theme is more like a long-term prospect that is interesting. Is about the fusion energy. Okay, and then we'll see more sectors. You see more and more applications of in the energy sectors in the near future. So for the power grids, the power grid is how electricity is transported and distributed, right? So from the how electricity goes from the producer, right? Like it's a nuclear plant to your house, right? To your home, or to the factory, or to the office, right? So this is the power grid, and it's a complex. It's a complex animal, right? To manage. This is not like only it's not like transporting water or even gas. Electricity is more tricky. And one big factor is the frequency. So there's the frequency on the power grid, and that frequency has to stay in a narrow range, right? It could be on that so 50 hertz or 60 hertz, depending on the regions. So in that study that I cite, you find a reference at the end. They use explainable AI, right, to quantify, predict, and explain the power grid frequency in 3 European areas. Right? So they have these 3 European areas: the continental Europe, Nordic area, as is the Nordic country, Sweden, Norway, etc. And Great Britain. So Great Britain is an island, right? So it has its own power grid. Right? It's not there's connection to the continental power grid, but by big cables, right? But it's not they're still managed independently. So the stability of the power grid frequency is necessary for the good functioning of the power grid, right? For the management of supply and demand, and the prevention of blackouts, right? So AI has, I gave previously some examples of how AI could be used, like for supply and demand, but it has a black box nature, right? Especially if you use deep neural networks that could present some security risk on the different actors or regulators who require explainability of the results. So why is the AI is doing this or that? So what they do is as data. So it is like in machine learning, you have like the thing that you want to explain, the target variables, and then you have a set of features, right? They explain the variables that they use to explain the target, right? So they try to explain these variables, the maximum frequency deviation within the hour. And so around that 50 hertz. How is that frequency moving? So you want that number to be low, right? You want to look at the rate of change, right? You want to look at the so the first one, sorry, that's the maximum frequency deviation, right? Then the third one is the mean square deviation. That's the standard deviation of that time series of frequency. And then the integrated frequency deviation. So it's kind of the sum of the changes, the integral. Right? So they have all these target variables that they try to explain. Right? Is they had like load forecast. Load is the demand, right? The demand of electricity. the scheduled generation, right? So what the producers plan to to generate. They had wind or solar power forecast, right? Because these wind and solar are more intermittent, so they might have a bigger effect on the fluctuation in frequency, right? If they're present or not present, they may have a big effect. The nuclear plant, a coal plant, usually they have kind of this like they have a baseline production. They produce the same thing day after day, most of the time, especially for nuclear plants. For natural gas, there's a bit more flexibility, but they would be the base, and so there wouldn't be too much of fluctuation. They have electricity prices, actual load. This is more like ex post variables, actual generation for production types, and RAM features. By how fast you go, you can produce electricity. And then so they use also indicators of time, so during the week, during the months, so there's the demand of energy might be different, right? During in the summertime, or in the fall, or weekdays, weekends versus working days, right? Might be different. So they use data for 2015, 2019. The model that they use is one of the most powerful models in machine learning. In fact, and you have especially you have like quantitative data. It's called the XGBoost. I won't go over too much in the details, but it's it should be maybe your default model. You use a quantitative variable. So it's pretty good. So it's a tree like machine learning models. So it uses like a family of trees. Also, it's a tree-based algorithm, and they add it adds like so it works by iteration. But it has like several iterations. Each iteration it adds a new tree, and then each iteration improves the fitting on the training data, right? And then there's a loss function, and these trees are optimized to minimize that loss function. So it's like I get that reference. You can have a look. For explainability, they use what they call the shape framework. It's called from the Shapley additive explanations, right? So Shapley was an economist. He was like a game theoretician. So the Shap values show the impact of each feature on an output, right? So it could be like day of the week, right? What is the impact on the output? And it's a global importance, right? So like is Monday important to predict the standard deviation of frequency, right? So so you're able to attribute a variable to say, okay, X% is due to day of the week, X% is due to wind power production, and so on. So in the next slide you have an example. So this is from that paper. So here this is the MSD, so mean standard deviation. So the standard deviation of the frequency, right? And you see different colors, right? So different sharp values. And so for continental Europe, right? You see that dark green, that's the load ramp, is a big factor. Then you have lighter green is the hour during the hour of the day, right? And then you have the purple, kind of unexplained, the residual, right? Great Britain, it'd be like their head price, right? So it's not surprising, because it's more by I think that in the UK market is more deregulated, so with more competition, so it's maybe more like decided by prices. So this is for the power grid. So there are a lot of interesting application of AI, and you'll see that more and more, and probably even at the retail level. At the retail level, what you are going to see is maybe you have like what they call a smart meters, right? Smart meters in Europe, it has been is very common. In the US, I think you start to see it more. So smart metering means that you have different prices depending on either your usage or the time of the day, or the time of the. So when the demand is low, the price is low. So at night, electricity should be cheaper than during the day, right? In some cities, it's not the case. Sometimes you have a fixed price, right? For the day and night, the same price. Weekends, weekdays, it's so you don't have that. But in Europe, because they're not as energy rich, is very common. So the smart metering is part of what we call energy demand response, right? So these are the paper like I'm using here. They're reviewing papers, so on energy demand response. So it's how users change their demand, right? On the power grid, on the how they change their demand, the demand of the electricity power system based on price, incentive, right? And the tariff they pay, or contractual signals that they receive. Right? It could be on your contract. Right? You could say, well, if you don't consume electricity between 8 a.m. on 5 p.m. When offices are open, you'll get a discount, right? You can have this kind of agreement. So high price will lower the demand, right? More incentive would increase the demand in some periods, right? And they can try to shift the demand to the night. So since you have the washing machine or you wash your dishes, so maybe they don't want you to wash your dishes, between 6 p.m. and 8 p.m. because everybody's doing it after they have dinner, but they want you to wash your dishes with a dishwasher after maybe 9 p.m. Right? So they can make it that cheaper. So there's 6 application areas of AI. So load price forecasting. So load is a demand on price forecasting. Load scheduling and control at the aggregator level. Load scheduling and control at the consumer level. So aggregators are people who aggregate demand, right? They're more like wholesaler, whole buyers. Design of pricing and incentive schemes. And load and customer segmentation. Right? So let's go over this. So the load forecasting, right? It's really like demand forecasting. So so it can include like the baseline, like load, the demand, right? Without any demand response incentives, right? But it can also include the load forecasting when you have signals, right? The effect of signals on demand, right? And the demand can be at the wholesale level or at the retail level, right? So models can be regressions, SVM, simple vector machines, or neural networks. This is load forecasting. Price forecasting, right? To complement load forecasting, for instance, so you can do price forecasting on the demands. So at the demand on the aggregators consumer level, so it means that you want to predict the demand curve, right? So given that price, right, what would be the demand of the consumer, right? Or another way to say it is the price. You can measure what they call the price elasticity. Right? How sensitive is the consumer to the change in price, right? So some consumer might not be very elastic, right? So they will change. The consumption is not going to change a lot if the price is changing a lot. Some might be more price elastic, right? It might depend on the time of the year. For instance, if you use a lot of AC, right? You start to pay $1,000 of electricity bill for big home because you run the AC in all the rooms. Right? You pay like $2,000 of electricity. Yeah, maybe you might be price elastic, right? Or the heating is the same thing, right? You don't have like gas heating or you have electricity reheating. In the winter, it could cost a lot, right? So you might be very price elastic. Right? So AI could try to help you forecast that. Load scheduling and control at the aggregators level. So so it's can help. So AI can help optimize and control, right? So the load of a portfolio of assets. Right? So you have, if you control different assets that can produce electricity, you can try to optimize. So, okay, which generator, which gas turbine should I call, right? And then you look at all the variables. You look at the grid, access of the grid, the system operators. You know, you have some rules. You know, you have rules of operations, the different the demand response system, right? Your long-term objective may be to maximize your profits or minimize your loss, right? So, for instance, when there's a peak demand, if you have a nuclear plant, you cannot ramp up production very quickly, right? You have to rely on, you know, like a gas turbine or even a diesel generator, right? So which are like more expensive to operate, but they can be started like very quickly. Operated, you can do like stop and go. Load scheduling and control at the consumer level. So more and more at the consumer level, you see what they call energy management systems, right? It could be your home, it could be a group of homes, right? It could be in a small community that you share like the access to the power grid, and you try together to lower your electricity bill cost, right? So the EMS, energy management system, has to be optimized in terms of signals for demand response, right? So you have to be aware that, you know, energy is cheaper at night or on weekends, and maybe you should, you know, tell your residents, okay, maybe you should hit the pool, you know, like on weekends or after 10 p.m., for instance. So you can optimize the consumer demand, the preference. It will depend on the demand, the preference, and the cost. EMS also very useful when you produce your own electricity, right? In some community, they have a solar panel on their roofs, for instance, right? So you want and you have the option of selling power to the grid, right? So you might want to manage that to optimize this. No? So when is a good time to sell electricity from the solar panel to the grid, or when is a good time to buy it, right? Because electricity from the grid is so cheap, is lower than the cost of producing electricity from the roof, right? Then, you know, it doesn't make sense to sell it or do the reverse. Right? So these kind of things could be managed by AI tomorrow. Design of pricing and incentive schemes, right? So you can so after, like, let's say building a demand curve, right? You can try to build like the optimal pricing, right? And the optimal incentives or contracts, right? To maximize like a provider's profit, so or minimize its loss. Last theme is load and customer segmentation, right? So here's identifying different customer groups who look alike, right? So to segment the markets and maybe differentiate the demand response schemes that you offer them, right? So so maybe in the community you can identify the big like energy consumers, you know, maybe because they have like say, heating swimming pools, or maybe they have many like EV cars and they consume a lot of electricity. Or some, or it could be like retail consumers versus small industries, offices, and so on. So all the data such as historical load data, bid offer, characteristics on the consumers, they're all factors or features that you can use to try to segment the market. Right? You can group them, try to group these consumers. So the last example is a very interesting example that I think comes from DeepMind. It's on fusion energy. So fusion energy is still in the research stage, right? But we are making, I think every day it seems that we have like some news that you're making breakthrough. So it's something maybe that might come maybe in the next 10 years. I don't know. It's but it's interesting example. So nuclear fusion, so is the process of making hydrogen isotopes, right? So the deuterium and tritium fuse, they merge, right, to form helium atoms, right? And in that process, they create energy, right? They emit protons and so on. They then they form. So when they fuse, right, they form a plasma, right? So this has to be done at very high, extremely high temperature, right? Sometimes like multiple times what is the temperature at the core of the sun, right? And thanks to magnetic fields. So you have a plasma, right? So you can put it on a table and so on. So it has to be confined, right? So they're confined in what they call a tokamak reaction chamber, right? In the shape of a torus, and they are kept in place with what they call magnetic controllers, right? So when because when this plasma at very high temperature is conductive, right? You can have it reacts to electrical and magnetic fields. Okay. So on the right, I put a picture of a tokamak. It's a base is an research one based at the École Polytechnique Fédérale de Lausanne, so in Switzerland. So, so big challenge here that the so the challenge is to how do you control that plasma? How do you make sure that it stays it's confined and has the shape and the properties that you want, right? So here the team from I think DeepMind and some other academic researchers use deep reinforcement learning, right, to manage these controllers. I think in the past we saw some example of reinforcement learning. And the method that they use is the actor critic algorithm. Right? So the particular name is called MPO, for maximum a posteriori optimization. So it has like two neural networks, right, in the actor critic algorithms for reinforcement learning. One that evaluates the value functions, right? So it means that based on value function is the cumulative sum of future rewards. So the rewards should be defined by the objectives, right, of on the here it'd be on the plasma, or it could be a position, right? For instance, if the objective is to run the plasma, the center of the plasma to have the particular position, so let's say coordinate X, Y, Z, the reward will be 1, or let's say again just 1 over the distance, or the exponential of or could be minus the distance of the core of the plasma to the target, right? So you want to maximize the reward, so you want to minimize the distance. Right? If I put a minus sign, that way I put the reverse. Right? So it could be one objective. On the actor algorithm, the second neural networks is an actor algorithm. In fact, it's called policy network. That policy networks makes the decisions. Right? So that policy networks, that neural networks, is controlling these magnetic controllers, right? And it will it'll be based on some on the environment state variables, right, captured by sensors, right? So here, this is from the paper. So you see, right, so you have like an actor that look at the actor, look at that. So you should look at that big the square, that big square. You have the actor, the environment, right, on the control policy, right? The control policy. So it is making the decisions. It's making like voltage commands here, the A, right? And the target is like T, is T, and the environment is like state variable, so it's like M. So the learning is done. So we'll go after that. But some of the learning is done in the simulated environment. It's not done on the real tokamak. But So that's why it's done by simulation, but they try to make it as realistic as possible. And but the control is done on the real hardware. Okay. Yeah, so that was saying, well, learning is done on the simulator and control is done on real hardware. So what they find is that the model can accurately control the characteristics of the plasma, is voltage control in real-world experiments. So they did it to that on the tokamak, where I saw you that picture at EPFL. But not only that, they could also control the plasma when it had like some weird shape. So, or for instance, if it was divided into two plasmas, or like when you have like droplets, right? So droplets mean you have like a big plasma and you have like small plasmas that in form of droplets, and they can control the two. This would be difficult to do with traditional control, right? The traditional control, they are more like almost like hard-coded, right? So the more hard-coded, so simple rules. They say, okay, if it's there, if this, do that. And but the AI, the deep reinforcement learning models, is much better. So you can just simulate these droplets, right? And it will learn the control to control the droplets, and then you can plug it into the tokamak and control it. So this kind of so the fact that it can design your algorithm on simulation, right? So it's a big plus because it's much cheaper, it's much safer. So to conclude, so you saw like in the first part that we talk a lot about clean energy, sustainable energy. So it's really like we need to go through energy transition, right? And you see these the kind of budget, the investments required in that sector, right? By 2050 is like you talk about like $5 trillion of investments every year, right? So this is like a be a good area. You're starting your career, maybe something you should explore, right? AI can help manage the transitions. We use that Peacock framework, remember, prediction, coordination, optimization, and control. So we went over some case studies. I mean, there are a lot of applications, but I find these are the ones that I chose personally. I found the most interesting about the power grid, energy demand, and fusion energy. Right, but you'll see more application of this type as like practitioners learn more about AI, and as your AI students learn more about energy sector. They find it's a cool sector to work in. They can collaborate or find a job there. Regulators too, as the utility regulators, energy regulators, become more familiar with AI. We can see the potential of AI. Okay, so I have added the reference at the end of the papers, the XGBoost. Also, XGBoost is a very interesting model. You can use a lot, and these AEA reports. Right? Go to their web page too, and so that's it. Okay, so again to stop recording.